5.2 area. So the whole point of 5.2 is to understand the summation formulas and doing some basic algebra. It's nothing crazy once you see the formulas, but the whole point is getting ready for 5.3. But oh, there's my pen. Oh, well, I'll use that one. But I don't want to use up too much time and make you do 5.3. We'll just move on to 5.4 and we'll call it a semester, I guess. The first thing is we have to understand what the sigma notation means. The sum of n terms A1, A2, A3, all the way to AN. Oh man, we're all weird. Is written as the capital sigma. So this means a sum from whatever index we're talking about. So if we're using i's, then it'll be going from I equals 1 to n. So A sub I would be like your sequence or the formula for this collection of terms. Excuse me. So this creates the terms, and this is telling you to add them all the way until you get to n. So you're adding the first one because it starts at 1, and you go all the way until whatever n is. Oh, look that weird again. A sub n. Okay, so let me write down each piece. All this rain is messing with me. Where I is the index of the summation. A sub I is the ith term of the sum. And the upper and lower bounds are n and 1 respectively. Whoops. Okay. So this example right here will pretty much explain it if it doesn't already make sense. This is telling me to sum. Let me use the index of k. Go from k equal to 3 all the way until 5. So this is the formula where I'm going to cycle those numbers through. There'll be 3 over 3 plus 2 plus, so I'm starting at 3, right? This is the part that's changing, the k's. or replaced by the index. And then you go to the next one, so it'll be 4 over 4 plus 2 all the way until 5. Does that make sense? Here's your formula. This is telling you which numbers to start at and where to stop. And it's telling you to sum them up.
Makes sense.
Okay. So they'll also expect you, so basically you'll just add them up, get a number, who cares? They'll also give you a pattern and they want you to create this formula yourself. Okay. So I'm gonna make one up here. I think it's from the homework. I don't remember. Wrote this earlier. Use a sum notation to write the sum. So you'll need to help me out here. Do you see the pattern? Do you see what is fixed? Do you see the beginning? Do you see the ending?
Yeah. So 11 would go on top.
What's that?
11 would go on top of the.
Yeah, that's like our end, right? Our ending.
Yeah. And
So we're going from, oops, yeah, 11. We're stopping at 11. Where are we starting?
At 3?
Let's see. The 3 is fixed all the whole way, right? So the 3 is not changing. It looks like the part that's changing is the 1, 2, 3, all the way to 11, right? So this piece is like your variable. And it starts here and it goes to 11. Does that make sense? We can call it K, I guess. All right, so now, so here that you were given this formula and it created this pattern. So here we're given the pattern. Can you find the formula? Well, for sure it's a fraction, right? So what I recommend when you're doing these, especially if you're going to Cal 2, this becomes important again towards the end of Cal 2. Look at the things that are fixed. Do you see how the 3 is not changing, right? And then there's this 2 that's not changing. So that has to go right here, right?
Yes.
And the part that's changing is your variable because it's varying, So this would be your K. So check if it works. If I plug in K equal to 1, does it give me the first one? If I plug in K equal to 2, does it give me the second one? That's all you gotta do, is just give them this. Okay. Any questions before I give you all the formulas you're gonna need? All right. Excuse me. Now here's the first one. The summation from 1 to n of just I. Basically, if I'm adding I all the way to some ending n, it'll be equal to the n times n plus 1 over 2. So if it's general, then you just use the formula. If it goes to like 5, then just plug in the 5 there. So you could skip, instead of adding all these little terms, just use this. Okay. If you're adding something that's squared from 1 to n, it has to be from 1 to some ending. It's going to be this, n times n plus 1 times 2n plus 1 over 6. Number 3, if it's cubed, you're adding a bunch of cubed terms. It's going to turn into n squared times n plus 1 squared over 4. All right, there's another one. If you're adding a constant n times, well, it's just n times c. That one's kind of obvious, right? Where c is any real number. All right. So you're gonna have to use these to do the next couple of examples. Uh, yeah, let's do the next one on the next page. It's kind of long. So the first few are just kind of finding the sums, so you can just plug in the number and get a total. It saves you time. Okay. So you evaluate this sum and then plug in, once you find the general sum, plug in these n's, and then you can get different totals. So you can say, well, let n go all the way to 100, 1,000, or 10,000. Um, this is I index. Yeah, okay. So what you can do, it applies to integrals as well. So if you have a variable that's not related to the index, then you can just pull it out in front of the summation. Because the index is equal as I. So now I just have I plus 1. You can also separate sum just like you can integrals, because integral is technically a sum. So all the properties of integrals are technically in the background. I'll put some brackets here. Okay, so you see how we separate it, right? Okay, excuse me. So you apply the formula, number 1 and number, I think it's 4, on each of these. So this will become 1 over n squared. The formula for summing the I will be just n times n plus 1 over 2 plus Cn would be 1 times n. So I used number 1 and number 4 from the last page. Does that make sense? Like we just applied the formula here. Okay. So now just add these fractions and plug in those numbers. That's it. So add these up, you'd get, well, first distribute. N times that would be n squared plus n. Get a common denominator, that'll be plus 2n all over 2, right? Add that together. Multiply the n squared in, you'll get n squared plus 3n over 2n squared, which will reduce to factoring an n out. to this, right? So this is the sum of this in general for n. Don't I just plug in the numbers? Who cares? This part is not interesting. Plug in n equal to 100, you get 100 plus 3 over 2 times 100, which is 103 over 200. Plug in 1,000, it'd be 1,000 plus 3 over 2 times 1,000. Be 1,003, oops, over 2,000. N equal to 10,000, same deal, skip this step. Be 10,003 over 20,000. So we found the sums for 3 different n's. But first, find the sum in general.
Oh, I see. We factored the n to get n plus 3. Okay.
Yeah, yeah. Are there any questions on these ideas? Okay. Have any questions on 5.2 before I move on? Does that make sense or is that okay? Sorry, I don't know if, okay. So let me know if you want to see another one or something. If not, I'm moving on. All right. Right, the rest will be similar. It's just depending on the equation, you'll use different formulas. And you might have to take a limit if they exist, just n goes to infinity or something. I forget. Or maybe the sum does. All right, final section. The fundamental theorem of calculus. Whenever you hear that in a math class, it's probably a big deal. Fundamental theorem. So if a function f is continuous on the closed interval a comma b, and capital F is an antiderivative of f on this interval AB, then integral from a to b of f of x dx is equal to capital F of b minus capital F of a. So basically, over some interval a to b, so the beginning of the interval a to up all the way until b, you integrate it or find the antiderivative, and then you plug in the upper bound minus the function at the lower bound. And this will find you an actual number, a value. So this is a definite integral. And this can represent all kinds of things like area and volumes and whatever. Just depends. But for now, let's just do them in general. So evaluate the definite integral zero to 4 of 3x minus 1 Okay. Okay. First, let's multiply it out because we don't have any rules, at least not yet, to integrate that. So y'all agree this would be 9x squared minus 6x plus 1. So now integrate term by term. Got the dx, darn it. Excuse me. Didn't get much sleep last night. Okay. So what I recommend is do the antiderivatives on each one, and then just put the bounds on the whole thing, 0 to 4. So this will be 9x 2 plus 1 over 2 plus 1 minus 6x 1 plus 1 over 1 plus 1 plus x all the way from 0 to 4. So this will become 3x cubed minus 3x squared plus x. Let's skip some minor algebra because I'm running out of space. So now evaluate, and you're done. So top minus the bottom. Minus the entire thing. So put some parentheses or brackets. Everything at 0. And this example is not going to matter because there you will all go to 0. So this is just 0. Who cares? Add all this garbage up, and you're going to get 148. Okay. Any questions on the mechanics here? Just integrate it, each part, find the antiderivative of each part once it's separated. Then plug in the top number minus everything at the bottom number. Okay.
Makes sense. Just a lot of steps. Can imagine like adding more to this, make it more complicated.
Yeah, the function, well, if you're going to Cal 2, you're going to see that there's a bunch of different ways to find antiderivatives. Like, you know how we had the product rule, quotient rule, and all that
Oh,
stuff.
yeah.
We have a bunch of them for these.
Oh man.
And then you saw the applications for derivatives, right? We had
Yeah.
rates of change, increasing and decreasing. We saw maximizing functions or whatever you want to maximize or minimize. These will all have a ton of their own applications, which is why they become important in like science and stuff.
Oh, okay.
The first major application is area. So when you have non-geometrical shapes, just really strange looking shapes, you can use this to find a almost exact area, or an exact area actually. Instead of just like, let's say you had a weird shape, it's not a triangle, it's not a circle, it's not a whatever stuff that has formulas, because real life is not shaped perfectly. So this will find you the area. You just approximate whatever shape it is with a function, and then you find it. And this would be the distance or the length or something. It depends. Depends what we're talking about. Okay. So here we go. Do each one separately. One second. Okay. So this will just be simple power rules, right? 1 plus 1 over that same thing, 1 plus 1 plus this becomes 2x going from 0 to 3. To simplify this garbage, get x squared over 2 plus 2x from 0 to 3. Plug in the top one first. Minus the bottom two. But this time, again, they're going to go to 0. So just add these guys. That'll be what? 9 halves plus 6. You need 21, right? 21 halves. Okay. So any questions on that? Is that okay or not too bad? What the fundamental theorem is asking you to do.
It's not too bad.
All right. Well, let's do an application and then I guess can call it a night. Okay, so this is one of the one of the first main applications. Um, it helps to be able to graph this stuff on Desmos to help you out or your calculator so you can see what's going on. Find the area of the region bounded by the graphs of the following equations. Okay, so this is the first equation, and it's the second, third, and fourth. So all of these lines and this parabola are going to enclose a little section and create a shape. The shape is non-geometrical, so you have to use integrals to find the area. So y equals 0, you agree that that's just the x-axis, right? The horizontal line. X equal to 3 is a vertical line at 3. This is the y-axis, right? So graph all of them. You start to create a little enclosed region. All right, so here's 3. Well, x equals to 3 in vertical line. Here's y x equal to 0 right there. So we got this section, y equal to 0. And then we have the parabola, right? The parabola is going to be something like this, going upward. So we have this section that's being enclosed by all these pieces. So if you're not an expert at graphing, then use your calculator or plot some points in this guy. And you'll see like, okay, I only really need this section because it's going from 0 to 3, right? I'm not looking at the other part of the parabola. Technically, it does that whole thing, right? It's a U shape, parabolic shape. But the reason we need the graph, the region, is because when you create the integral from A to B, it has to be the top part of the region minus the bottom. So this is the top, this is the bottom. Okay, so the top is the parabola equation. The bottom is y equals to 0, so just put a 0. So if it was like another function, you'd put you'd minus some other function, the entire thing in parentheses. And then since we're doing dx, right, you basically imagine little rectangles, because that's what the integral is. You're summing up a bunch of infinitesimal rectangles. So the width is on the x-axis, right? It's going this way. It goes from 0 to 3. Does that make sense? You see how we use this graph to determine the top and bottom, where the bounds of integration are going to go, right? 0 to 3. This is the entire section. And since it's a vertical rectangle, it's going this way. It's just, you only look at the x. So from here to here. So if we're looking at the x, that means it has to be dx, which means everything has to be in terms of x. It's all connected. Once it's set up, it's just an integral we've done before.
So you put 3 at the top because it's x equals 3 there.
One more time.
You put 3 at the top because x equals 3 for that second x.
Yeah, we're
Okay.
integrating from 0 all the way till 3. So this is the section that we're going to find the area of. So from here to here. Let's go ahead and integrate it. I'm not going to show the separation this time, but So that'll be 2x cubed over 3 plus x squared over 2. That's 2x from 0 to 3, which will be oh shoot, hold on. This mosquito keeps biting me. Dang it. I hate when they get right underneath your desk. It's the worst. Oh, okay. Right out of space. This will go to 0. Add these guys up, and you'll get 57 over 2. So let's graph this on Desmos. You can see it better because my graph is garbage. Okay, let me try to zoom in a bit. Okay, so here it is, right? There's a little section. You have the parabola going on top. You have the bound y x equal to 3, x equal to 0, and y equal to 0. Right, this is y equal to 0 right there. X equal to 0 going this way. X equal to 3 going that way. Nothing crazy. So we know that we're going to find the area underneath the curve. That's what we're doing. You can approximate it using a triangle formula, but the accurate formula will come from the integral, accurate area. Any questions on this idea? Okay. But yeah, I advise you make sure you graph everything because it'll kind of set you. It'll show you how to set up the integral. You guys need any extensions? I don't know if anything's closed on y'all. Yeah, guys doing okay?